This is session 22 of the series on the Orange Pi 5 Plus, and we've been doing graphics. This session will be on the Spirograph little toy that you may have at some time in your life owned, had as a kid. It came out in 1965, and maybe you still have it. Get it out and refresh your memory. So let's start out by first looking at what a circle is. A circle is just the location of all points equal distance from a center. So here's the center, and then if you go out in any distance from the center, and if you go out a distance equal to the radius of the circle, you will encounter the edge of the circle. The diameter of the circle is defined as going from one point through the center in a straight line to the other edge, and that distance is the diameter of the circle. The distance, if you start here and go all the way around the circumference of the circle, the total distance from one point back to the point around the edge is equal to the value of pi, which we beat to death earlier in the series, but it's 3.1415926.5, etc., times the radius squared is the area. That's this enclosed area, everything within the boundary of the circle. The circumference, I'm sorry, I may have slipped there. The circumference, the distance around the circle, is equal to pi times the diameter. It's also equal to 2 times pi times the radius, since the diameter is twice the radius. So basically the spirograph is going to be doing things based on the circle. Let's talk about angular measurement. If you have two lines joined at one end but separated, they are separated by this area in between, and we call the difference between here to there. If we rotate this line about the center, we call this the angle of separation between the two lines. You've probably all your life used degrees as a measurement. This is, from here to here is 35 degrees. If this line was vertical, then we'd say the two lines are at right angles and that the angle is 90 degrees. But there's another unit of measurement called the radian. And the radian is defined such that if this angle measured in radians times the radius is going to be equal to the distance from this point along the circle boundary to this point. So by definition, this angle in radians is defined to be the number times the radius that's equal to that distance. Don't know if you remember, if you look at it, if you still own a handheld calculator, such as Casio or Texas Instruments, whatever, on the trigonometric functions like sine and cosine, you have a choice of entering the value in degrees or radians. In C, the program in C, in the functions cosine and sine require the argument to be in radians. It's just the way the algorithm is written. All right, let's go back to the spirograph. The spirograph, you have a large frame that has an open area, fairly large, and it has teeth along the edge. Okay, why did you skip there? Something. It has teeth along the edge, and then you have little discs of different sizes that have holes in them that you place in the middle, and then move it to the edge so that the two edges, the inside edge of this circle and the outside edge of the little disc, mesh. The gears on the spirograph keep the disc from slipping as you move around the circle. There, I did it again. I just moved the mouse. Anyway, the way this thing is constructed, first of all, the frame, the outer circle has a radius of R1. And depending upon who made the spirograph, it has different diameters. You can get small ones. I think there's a small one for portable use, and then there's a large one that you need a desk area to work with. Then there are various size discs, and each one has a radius. We're going to call it R2. I drew it in purple here to ease the demonstration and the illustration. And then there are a number of holes. I just picked one of them here that we're going to insert the pencil or pen or felt tip pen, whatever your writing device you use. And it's located at some distance R3 from the center of this disc. This distance from the center to the center of the little movable disc is D1, and it's easily calculated to be the total radius from the center of the big circle minus the radius of the little rotating disc. The process of drawing a figure, you insert the pen in this hole, then you start rotating in this direction, and the pen will move along a circle here to the, at some point, and it will rotate as long as it's in contact with the outer edge, will rotate without slipping. That's the purpose of the gears, all the way around to this point. Now it's in contact with this red area all the way around. Now this red area, its distance is equal to, using our little radian formula, is equal to this angle. In this case it's pi over 2. I went 90 degrees. So this is whatever theta times R1. So that's the distance covered in moving this disc from here to there. Well, whatever this distance is, because this disc is rotating in contact with it and without slipping, then the distance covered around this disc going to here has to be equal to its rotation angle times R2, its radius. So these two numbers are equal. This distance and then the distance around here in contact, those are equal. If we solve for theta, which is the angle this disc has rotated to get to here, that theta is equal to this angle, pi over 2 times R1 over R2. Now since R1 is greater than R2, this means that this thing has rotated more than 90 degrees. And I think you can expect that, and it's obvious because this is a smaller disc. It has to go get this distance, it's got to rotate more. So that's the formula. If I take, for this drawing, I had R1 is 900. That's just my units. You can say 900 millimeters, whatever. And R2 has a radius, or the small disk has a radius of 250. So for rotation angle of the small disk, it's equal to theta 1, whatever angle you move here, times R1 over R2. So that's our little formula. To write the program, I now have everything that I need to draw the path that this hole is going to follow and going all the way around here. Oh, and I drew this. If you work this out, did I do it? I didn't do it. I didn't do it. But this rotation angle here is from here to here is 0.9. Do the math. Theta 1 is pi over 2. This is 900 divided by 250. You'll find out that theta is equal to almost, well, it is 9/10 of a revolution. And so I drew the moving disk placed here. This point on the disk would wind up here, and P3 winds up here. Now this looks like 90 degrees, but it's not. It's 1 degree. Now to write a program to simulate what's going on here, I need to input the following data. R1, the radius of the big disk, or big circle. I need to input the diameter of the radius of the small disk. I need to input the distance the pin is from the center of this movable disk. Now when you put the disk inside here and move it against the edge here, the hole that you pick is not necessarily in line with P1 through the horizon. So it starts with some angle offset, call it theta 2. That's the original offset. You could, take the disk out, rotate it enough, and then get it where P3 is on this line. You see what I'm talking about? I need that. I'll just input that offset into the program. To draw a figure, you need to go around several revolutions, because if I start here and I go all the way around and draw the first part of the figure, when I get back to here, unless there's some miracle occurring, P3, the pin will not wind up at this point where it started. It'll be off somewhere else. You say, okay, I'm not through yet because they don't match, so you'll go around another revolution. And you'll do this until it lines up or until you quit. There is the possibility that it would take 100,000 revolutions for it to get back to the same point. You're not interested in that because by that time you've run out of ink and filled up the circle. So what I do here is, I don't know how many revolutions to make, so I'll just input a number here, the number of times I want to go around the circle to draw the figure. Now, because in DXY2PS I modified it that I could do any color line, I'm going to set the color of the pin to RGB values. So I have 17 million plus colors that I can choose from. You cannot go to your little Michael's or Walmart or whatever and buy enough pencils and pens to get all the colors. And then I also have an infinite number of pen sizes. Well, I've got 8, but I could change them. So that's my input to the program. Program goes and calculates D1 equal to R1 minus R2, using my secret formula here. Then what I'm going to do is I'm going to take theta 1 and start it at 0, and as it increases, P1 moves around here, and then I'm going to calculate where the pin is when the disk is at that position. The way I do that is I'm going to do a loop, generate theta 1 equal to 0 all the way around to the number of revolutions times 360. One revolution goes 360 degrees. I'm going to convert this angle inside to radians. Theta, the rotational angle of the disk, is equal to theta 1 times R1 divided by R2. There's a secret here. When I push the disk in this direction, it rotates in this direction, clockwise. In mathematics, a counterclockwise rotation is a positive rotation. Clockwise is negative. So there's a negative sign involved here on this rotation, and that's very important. I did it once before. When I first did it, I forgot about the negative sign, and the figures turned out differently. You'd have to, program another machine to do it, to rotate in the opposite direction. So I calculate theta. Now, the point where P1 is equal to D1, this distance, times the cosine of theta 1 for the x value, and the y value is D1 times sine theta 1. So as you see, as this goes up, cosine decreases. It goes to 0 here. So the x value along the x-axis is 0, but the y value increases because it goes as sine theta. Sine theta here is 0, so the y value is 0. But as you go up, it goes to 1 times whatever this length is. So that gives me the position of the center of the disk. To find out where the pin is, it's equal to P1, the position, plus R3, the distance from the center, and it's rotated by angle theta, which I calculate here. But it was already offset by theta 2, so the total rotational angle is theta plus theta 2. So now I have the point where the pin is, at point P3. So I'll calculate P3 for X and Y. For the plot routine itself, okay, what to do with the pin and feed it to dxy to ps. If theta equals 0, I want to move there, because remember when you start the program, it's in the home position, so I'll move it there. Then I draw a line. Well, if I draw a line from P3x to P3y, that if I go from point P1 to P1, it doesn't do anything. So it's a no-op the first time, but after that, the new value of P3x and P3y, the new xy position, is different from what I drew the last point. So this will get us a new line and will hopefully get us a smooth curve. See this curve here, the one for the outside loop, for the outside circle? It's done in 1 degree increments. So there's straight lines, there are 360 straight lines that make up that circle, but it's fine enough that your eye doesn't see it and the screen doesn't render it enough or whatever. So that's how I did the program. So let's look at it. Let me go to Spirograph. Clear that out. So you can see here's my program. So let's just take a quick look at it so you can, if you are following along here on some system. First of all, we have a standard IO, and I need the math.h because I got the sine and cosine. I always put standard lib in there just in case I want to use the exit. Now I have my little drafting functions that are all one line for using DXY to PS. Remember I did this in the last lecture 21 when I did the squares and I did the arrows. So there's a home, move, and draw. That's these home just prints out a capital H. To draw, you output the letter D, followed by two numbers separated by a comma. And I had that scale factor in there, but I've got it set to 1 for this program. And then for the move, you just do an M followed by X and Y. Now, I showed you how to, how we're going to draw a curve, okay, with a pen. Well, if you had a spirograph and you put one of the discs in there and you went around a couple of revolutions and you could pull the pen and the disc out, put another one in there, use another pen and draw another curve on top. In order to do that in this program, I have to input how many curves do I want to draw. Do you just want to draw one, or do you want to do 2 or 3? And for each curve, you input the values for that curve. The R1, the big radius, the radius of the disc, the distance from the center of that disc to the pen, the offset angle, the number of revolutions I want to draw, I'll show you that. Then my RGB, what pen did you use? And then I can have different pen widths. I can have a Sharpie, or I can use a real fine point felt pen, and I can use any color I want. Now you do realize, of course, that because of we're using the computer, I have more combinations than you can ever go through in your lifetime. There's no computer alive that has enough computer power to go through all these, because there are, this is 32-bit, so I can go whatever it is. That number cubed. The angles can go from 0 to 360. The number of revolutions can go from 1 to N, where N is large. And then the color combinations are 17 million. And then pen sizes, I've got my program set up for 8, but I can get it set up more than that. So there you go. All right. In my little DXY to PS, remember I modified it to put the color in. So I have color for pen 10, output the colors RGB. For the pen size, I just put J and then a number between 0 and 8. Now we're ready to do some calculations. So D1 is R1 minus R2. The for loop here says start with theta 1. We're going to start the right-hand side, put the little disc on the right-hand side. That angle is 0, and then we're going to go up to and including N rev, number of revolutions, times 360. So if N rev is 1, I'm going from 0 to 360 on the center of the little disc, and it's going to go from theta equal to 0 to 360 times that, times this figure right here. But anyway, you're going to generate 360 thetas. They'll go from 0 to 2 or 3 times 360 for one revolution of the pin holder. Calculate P1 position is equal to D1. That's the distance from the center to the center of the little rotating disc, times cosine. This is my factor of pi over 180. By the way, you don't have to memorize the value of pi. You just use the arc cosine of -1. that's equal to pi. So pi over 180 is a factor to convert degrees to radians times theta 1, which is this angle, in degrees. So now I get the starting point, and then relative to that point, P3 is that point plus R3, that distance from the center of the disk, times cosine, changed to radians, theta plus theta 2. Theta 2 was that offset. So this will give me P3x, and P3y is P1 minus. Now the minus comes out because these angles, ooh, a boo-boo. All right. Oh, man. It's a good thing let's see here. Let's see. What's this? All right. FACTOR times that. Okay. No harm, no foul. So that's why I have a little duck on my desk that I talk to. You'll think I'm nuts, but it just helps debug programs. Also, showing them to somebody else helps also. All right, so now I've got the point where the pin is, so I just draw it. Now, if theta 1 equal to 0, okay, I haven't drawn anything yet. The pin is at the home position. I need to move it, so I move it to P3, Py, and those are integer, so I convert floating point to integer. Just round it off, and then draw. So the first time you move to the point, then you draw to the point, that's nothing. But after that, the pin's at an old point, and I'm going to draw to a new point. So that's the end of the drawing curve. So I draw one curve, and if there is more than one curve, then I come back, read the new values, okay, and draw that. Now I have a script that compiles a program, and this is where I saved my bacon here, and that I had a slight error in the program. I corrected it, so now when I run it, it's correct. So this generates a new Spiro, move that to my bin directory. Now I run Spiro, the program, on the input file, which we're going to start off with run 1, and then that's going to convert my little plot, the little path of the pin into DXY commands. And this is, I'm going to type the name of the shell followed by run 1. So this says the first argument is run 1. So it says run Spiro, input run 1, and then take the output, run it, put it in run1.dxy. Then I come around here and do dxy to ps. Now, one of the things I guess I forgot to mention is we obtained HPGL 2PS, which contains that program plus dxy 2PS from C10 and from GitHub. C10 had a file called dxy2ps.man. You need to copy that somewhere because that's the man page on how to use the program. And if you run man on that, the options on DXY are you can scale it. Instead of me scaling it inside my own program, which I can do, and then if that's not enough, then I can scale here up to 3. There's a limit on 3, and that's just because it was written for mechanical plotters. I can also offset the starting home position on the page by going up over 100 and up 100. I don't really need to do that, but let's just leave it. And then this inputs the run1.dxy and then creates our PostScript file, and then we can view it. So I've got run 1. Let's do run 1. Let me show you what run 1 is. Okay, let's do just one curve so we get familiar with the program. D1 is 900 units. the little disc that we're going to put inside is only 1/9 of that. It's 100 in diameter. I'll move the pin is over 30. Excuse me. Yeah, so it's close to the center. The offset angle is 0. And I've got 20 revolutions here. Let's start off with a 1, and I'll set the color to purple. 1 red, no green, 1 blue, and the pin size is 1. So if I do shell, run dot shell, because I didn't make it executable, and I run it on run 1, this is going to input that to my Spirograph program, create the PS. And because I've had a small value here, it draws almost a perfect circle. So here you can see that the ending position is not the same as the starting. So let's try to go a little further. So I'll VI run 1, and let's go like 8 revolutions. Run it again. It's not very interesting. Let's see if let's add another curve here. I'll go to 2. Whoops. And let me move this up here. So now the second curve is also 900 for D1. Get a larger disc, move it closer to the edge, offset 45 degrees, and do 50 rotations. Oh, that's too many. Let's start off with 5 and see what happens. Now I'm going to make it red. Run the shell again. And now we see what red is. Now there's the starting value, there's starting red, and then here is the ending. So I do need more. Let's see, this looks like it's going what? What's it doing? Oh, it's starting here. It's moving up, and it's going to go around, and this is how far? Let's do it about 4 times that. So 4 times 5 is 20. Let's go 20 revolutions and see what we get. Oh, that looks pretty interesting, doesn't it? Oh, you remember my little case where I said we could do white? Let's, instead of just delete this line, let me make it white. 1, 1, 1. Now, so the purple one will disappear. That's pretty nice. Now, one of the things we're doing here is we're using our Orange Pi 5 Plus, and we're going to generate an infinite number of beautiful spirographs. Now, if you find one that you really, really love, and you do not have a printer, then hopefully you have in your possession a USB thumb drive. Then take the PDF or convert the PostScript to PDF. There's a routine to do that. I'll show you. You can take the PDF down to your Office Max or Office Depot or whoever, or maybe you can take it into your office and you can print it out on a color printer. Then you can frame it and put it on the wall and just brag about it. Now, even though this point here is not matched up, you'd have to be super critical to look at that. I don't want to mess it up. Well, I'll mess it up. Anyway, you can print it off if you want to. Let's VI run 1. And this thing was 20. Let's make it 30. Now, there's a possibility that this gets too complicated. Simple is beautiful. Still got this one little point here that won't go away on me. But that's beautiful too. It's just a fancy little donut. Well, now, okay, let's see how am I doing on time. I'm having so much fun here. Yeah, 35 minutes. Let's do this. Let's do 3 curves. Let me put the purple one back in. Now this one, okay. Something else you might not be able to do with this real physical spirograph is change out the holder, the template, whatever you want to call the big circle one, the guide to the smaller disc. You can change it out to a smaller one or a larger one. I can make a spirograph as big as the solar system. But I'm going to switch in a smaller spirograph that has a D1 of only 300. I'll still use my little 200 disc. Oh, a little secret here. What happens if the small disc is equal to or larger than the frame? Won't fit. Won't move. All right. So let's try this, and I made it black 0, 0, 0. I'll increase the pen size here to 4. Let's do this one with thick pen. Let's do this one 2 and this one 2. And I can instantaneously redraw everything. So I'll do run.sh to run 2, run 1. Oh, I didn't see that coming, but that's pretty nice. So you now have the tool. I have written for you. You didn't have to do too much. I've written for you a tool that you can now go and generate some beautiful graphics. I do good work. I've got a couple more examples here. Let's try those. VI run 2. This one's 900, 200, 150, that's close to outside, offset 45. Let's do this. Let's offset 0. Do 50, no, let's do 30. This is purple, but it's lighter color, pen size 2. So shell run.sh run 2. What? I'm drawing donuts here. Okay, now I had a donut here. Let's set the offset here to 45 to see what the offset does to the nature of the curve. You expect some change? Not much. We got an infinite number of, let's see what run 3 was. This is 900, 300, larger disc, halfway in between, offset 0, 25, and this is red. Donuts. I think you just have to, you've just got to run these and see what you get, and then experiment with the values. So run 4. Oh, that one's a green one, and I got a larger donut. I'm gonna take a chance here. Then I'm gonna let you go. CP run 4 to run 5. VI run 5. We'll leave it green and everything, but let's make this thing very larger than I can't make it larger than the diameter, but I can make it larger than the radius. Let's make it 14. Let's make this 4. Let's see what it does. I have to think about it, so I don't want to think about it. I'll just run it. Whoops. Oh, this is a new one, so I need to rotate this. little green heart. Let's see, did I have an offset in there? I did. Let's change that and let's see if that heart gets more upright. How do you like my English? Oh, it rotated it. So you have to play with the offset value. Since 45 got it almost vertical and 0 gets it too far to the right, then I'm guessing that this needs to be closer to 45, but not quite. Almost, I'm almost there, but you see what you can do. Now I've got this heart, and I can put another heart in the middle of it, or it's open season on experiments. Now, got a little open end here, but it's okay. It's going to just go forever. So, that's the end of the Spirograph. I hope you enjoyed this. I'm sorry it took more than 30 minutes. It took 40 minutes. But you learned something. You've got a new toy. And this is not the only thing. By having the DXY to PS, it opens up a lot of territory for you to be creative. What was the other thing that I was fixing to mention? That's it. Mine went blank. Again, does that a lot. All right, thank you. Hope you learned something. Find some more use for your computer. And we'll be using DXY to PS to do some serious graphs later on. I'll come back to it. Thank you. And hopefully you can copy the program. I don't care whether you're using an Orange Pi 5 Plus or not. Hopefully you're using Unix so you don't have to convert everything to some other system and try to run down programs. I'm interested in I see that from the YouTube videos that everybody's getting all excited about the Raspberry Pi 5, but we've got a system that's more powerful and consumes less power. I'm concerned that I'm not concerned because I'm not worried about it, but it's everybody else's business. But the Raspberry Pi 5 requires a 27-watt power supply. I want somebody to take the USB power meter like I've done on the Orange Pi 5 Plus and the Lychee Pi 4A. Both of them run less than 6 watts at full power. Measure the same power on a Raspberry Pi 5. Must be significantly higher. Okay, I wonder. Let's go. Talk to you, lecture number 23. I don't know whether to call these episodes, lectures, or what. I'm done. Thank you.